Hey everybody, in this lesson I'm going to define electromagnetic radiation, talk about wavelength, frequency, and energy, which are some ways to describe this radiation. There's some mathematical relationships that connect these variables, and we'll also touch on the idea of quantization. Let's start off and just define electromagnetic radiation and what it is. It can be kind of difficult to understand because it's not immediately recognizable, so just kind of go with me here and you'll eventually be able to piece this together. But this radiation, they are waves. It's one way to think about it. Technically, waves of something known as the electromagnetic field, and they propagate through space and carry energy. If you're wondering what it means to propagate through space, you can sort of think about it as, waves in the ocean propagate through water. Sound waves propagate through air, the actual atoms in the air. These waves are more challenging to understand because they are propagating through space itself. They also carry energy as they go. We know the speed of these waves. It's the speed of light, 2.99 times 10 to the 8th meters per second, extremely fast. It's going to be an important number later on. Make sure you take a second to jot it down. And when you're talking about these waves, it's important to know that there's lots of different types of them. There's a whole spectrum of different waves, and you can think about that spectrum as being grouped based on how long the waves are. Some are really, really tiny. Some are really, really huge, and that gives us all these different types. If this whole time you've been saying, what even is this electromagnetic radiation? Have I ever seen it before? You have definitely seen it before. You just didn't know probably that's what it was. I'm talking, of course, about visible light. As you look around, or as you're looking at the computer screen or phone where you're watching this video, you are seeing light. Almost our entire human experience is based on our observation of visible light. And visible light is just one very specific, teeny tiny little piece of this larger electromagnetic spectrum. The chart you see on the that we're looking at now shows all the different types. The type that human beings can see with our eyes is just this teeny tiny little band right here, and these diagonal lines kind of break that out into the colors that we're used to. But red, orange, yellow, green, blue, violet, that's the spectrum of visible light. That is one type of electromagnetic radiation. There's other types you might recognize, like ultraviolet, things that we can't see with our eyes, but we're concerned about as humans because it can damage our skin or our eyes. That's why we wear sunglasses or wear sunscreen. X-rays, the things that let us get images inside our body. Gamma rays we don't come in contact with too often, luckily, because they're very energetic and dangerous. Infrared light is a different type of light we can't see. Microwaves, the type that we use to heat up our food, and radio waves that we use to do all kinds of stuff, like carry cell phone messages or Wi-Fi. Those are all different types of electromagnetic radiation. Just an interesting fact about this piece of visible light that we can see: if you took the entire electromagnetic spectrum and stretched it out to the length of the United States, the piece that would be visible to us would be about the size of a dime. That's how insanely small a chunk of this spectrum visible light is. Just kind of an interesting to put that in perspective. So let's back up a little bit and talk about waves in general, because this radiation, it travels in the form of a wave, and you've got to know how to describe waves, and there's three ways you can do it. One is the wavelength, and that's marked out on this diagram here. If you went from one peak of the wave to an adjacent peak and measured that distance, that is called the wavelength. Easy to define and remember because it is literally the length of the wave. There's also the frequency of the wave, and that is how many waves pass a given point in a certain amount of time. And generally that time is 1 second. So if you imagine these waves are traveling in this direction, and you chose a point, and I'll just draw like a vertical line to represent that point, and you literally just counted how many of these waves passed this line in 1 second, that number, so let's say it's 10 waves in 1 second, that's the frequency. It would be 10 waves per second. There's also the amplitude, which is the height of the wave. We're not going to get into that so much in a chemistry class, but those are the three ways that you can think about as describing any particular wave. Generally, a chemist is worried about the wavelength, which, by the way, we symbolize with this Greek letter, the frequency, which we symbolize with this Greek letter, and the units that you're going to have to use to represent these. You can technically use any unit you want, but when you do calculations with wavelength, they're all going to be done in meters, symbolized with a lowercase m, of course. In frequency, because it's the number of waves per second, it's often written as 1 over seconds. 1 over seconds is the same thing as the more common term, something known as hertz. You might have heard of the term megahertz. If not, that's okay. Hertz, though, is the same thing as saying 1 over seconds. The point is, wavelength and frequency to a chemist are super important because there's some important mathematical relationships that connect these two things, and that will have importance for us in understanding atoms. So let's first define this mathematical relationship that exists between frequency and wavelength. This works for any electromagnetic wave. The equation is given to you here. I'm going to label each of these pieces. If you take the wavelength of any wave, so there's our wavelength symbol in meters, and you multiply that wavelength by the frequency in hertz, or 1 over seconds. Any wavelength times any frequency for a given wave will equal the speed that the wave is traveling. 10.99 times 10 to the 8th meters per second. That number, of course, is the speed of light. So it's a really cool thing that is true for any section of this radiation. Besides being interesting that this is true, it's also really helpful because it can allow us to calculate back and forth between wavelength and frequency. For example, if you, say, took the microwave that is in your kitchen, and you can find this information usually on like the inside of the door, it'll tell you the frequency of the waves that your microwave is using. And I just pulled this number out as a common example, 2.45 gigahertz. You could actually find out how long those waves are. You could solve for the wavelength by using this equation. I'm going to write it out up here so you can see what it would look like. We can do this because that C value is a constant value. It's the speed of light, 2.99 times 10 to the 8th meters per second. So you'll always know the speed of light. Here we don't know the wavelength, so I can solve for that like it was the x in an algebraic expression. And I can solve for that wavelength because I know the frequency. The only challenge with this microwave example, and as you'll see a lot, is you've got to make sure the units match up. Your frequency has to get plugged in as just hertz, not gigahertz like you were provided with. So sometimes there's extra conversion steps that you've got to do beforehand. Here, if I know it's 2.45 gigahertz, and I just looked up the conversion between gigahertz and hertz, you're welcome to do the same. 1 gigahertz is 10 to the 9th hertz, so I just have to multiply 2.45 gigahertz times 10 to the 9th to convert that into hertz itself. I'm going to write that in scientific notation because the answer is 2.45 billion, and that's a lot of zeros, so I'll just write it as 2.45 times 10 to the 9th hertz. The point is, if I plug that in, 2.45 times 10 to the 9th hertz, and I do some simple algebra here, since this is just multiplication, I'll divide both sides by that 2.45 times 10 to the 9th, 2.45 times 10 to the 9th. It's going to cancel it off here and leave me with wavelength equals 0.122 is the answer my calculator gives me. And the units on that, remember wavelength, as long as you've done the other units correctly, will be in meters. So about a tenth of a meter is the length of the wave that is going through your food to heat it up inside the typical United States microwave. So that's one of the mathematical relationships. We're going to get to one more, but first, there's the very strange idea of quantized energy. This is an extremely complex topic that we're just barely going to touch on in this particular lesson. But it's important to have some idea that when you're talking about matter and atoms, as you typically are in a chem class, atoms is usually where electromagnetic radiation comes from. Any of the light that you're looking at right now is coming from atoms. If it's light from the sun, it's the atoms in the sun that are giving off that light. If it's the computer screen, it's the atoms in the computer screen giving off that light. It's from a light bulb. It's the atoms in the light bulb giving off that light. And when atoms do this, when they give off radiation, one of the stranger things that you observe is that these atoms only give off certain quantities of energy, right? If you're looking at a sample of atoms, they might give off this much energy here, and this much energy here, but they will not be able to give off the amount of energy in between that. You just see these certain quantities of energy that are observed. That's where this term quantized energy comes from. Scientists noticed this, of course, and theorized that maybe these quantities of energy exist because electromagnetic radiation only exists in certain quantities. And they call them quantized, sometimes described as little packets of energy. And all of this leads to the idea that electromagnetic radiation can also be thought of as very tiny particles called photons. This is the very bizarre thought that electromagnetic radiation can be thought of and is both wave and particle all at the same time. If that seems strange to you, then you're absolutely correct. It's a very strange idea, but it's true. EM radiation is waves that travel at the speed of light, is also particles traveling at the speed of light. Those particles are called photons. Essentially, a photon is a particle of light or a particle of microwaves or whatever it is. And that gives our last mathematical relationship known as Planck's equation, where the energy of a photon can actually be calculated. The symbol for the energy of that photon is the capital E. Sometimes I like to write a little subscript, E photon, because that's what we're going to be solving for here. To solve for that E, or that energy, you have to know the frequency of the wave in hertz, or 1 over seconds. And if you multiply that frequency by this number called Planck's constant, which is a known value, 6.626 times 10 to the negative 34 joules times seconds. If you multiply your frequency times that constant, you'll end up with the energy of one single photon of that type of radiation. So here's Planck's constant. Again, it's an important number. Make sure you write it down. We'll close this with an example to show you how this would work. This question says, a photon of green light from a high-energy laser pen has a wavelength of 540 nanometers. How much energy does this photon have, or does one of these photons have? So if I need to solve for the energy of a photon, that means I've got to use this equation. That means I have to know the frequency. So that's one of the challenges here is that in this example, I wasn't given the frequency. I was, however, given the wavelength. So this is going to be sort of a two-step process where the first thing I'm going to do is use the speed of light equation from before to get the frequency, and then plug it in over here to solve for the energy. As one added issue, I wasn't told the wavelength in meters, and that's the unit that you're supposed to use. I was told the wavelength in nanometers, so we have to go one extra step and turn my nanometer wavelength into meters first before I can even start the math. The conversion from nanometers to meters, I looked it up, it's right there. I'll just multiply nanometers times 10 to the negative 9th to find out that my wavelength is 5.4 times 10 to the negative 7th meters. Now I can plug it into my speed of light equation. Remember, we know the speed of light is always 2.99 times 10 to the 8th meters per second. The wavelength, now I know, I can plug in, is 5.4 times 10 to the negative 7th meters, solving for the frequency. If you do that algebra to solve for the frequency, you get 5.537 times 10 to the 14th. That's dividing the 2.99 times 10 to the 8th by 5.4 times 10 to the negative 7th. Now that I know the frequency, I can come back and plug it in over here to finally solve for the energy of one photon of this green light. Remember, H is a constant, Planck's constant, 6.626 times 10 to the negative 34 joules seconds, joules times seconds. My frequency now I know, so I can plug that in. And at this point, it's just a simple multiplication of those two numbers to get the energy value. If you do that correctly, you'll get the very small number, 3.67 times 10 to to the negative 19. It's a very small number because it's one very small photon. The units of this, the frequency was 1/seconds, so the seconds cancels out, and you're left with just joules. And joules is a type of energy unit, so this all checks out. And that is our final mathematical relationship with Planck's equation. That also wraps it up for this lesson. Thanks a lot for watching.